number 32, how to write the electron configuration of a specific atom. So again, we're going to ask for a specific element, and right here, oh, sorry, erase it.
I was going to make some space.
Okay, and you're going to write the electron configuration notation, and by that we mean the 1s2, 2s2, 2p6 stuff. If you listen to the song on Moodle, which we probably have inflicted upon you during class anyway, you know that it's all about 1s2, 2s2, then comes 2p6.
That's too long.
Yeah.
We'll do boron.
We'll do boron? Okay.
Okay, so we've got 1s up, down.
Yep.
Just for the sake of review,
Yeah.
what's up with the up, down?
Well, you got to spin in different directions.
Yeah, you got to
Otherwise
spin
they
in
can't
different
be
directions.
together.
That's right. These two electrons occupy the same orbital,
Mm-hmm.
but do they have the same set of 4 quantum numbers?
No.
Whose rule is that?
That is, it sounds pretty exclusive. I think that's the Pauli exclusion principle.
principle. Right. And then we go to 2s, and we get an up, down.
Mm-hmm.
And then we go to 2p,
With 3 sublevels.
3 different orbitals.
Yeah.
Yeah.
3 orbitals.
3 different orbitals, right?
Yeah. Px,
Yeah.
Py, Pz.
And then we have up.
Wait, how many? I think that's all the far you gotta go. Because boron is element number 5, and if we count from the beginning, because this is alphabet, we're building up from the beginning and so on. 1, 2, 3, 4, 5 electrons. Good.
Done.
Good for boron. What if we wrote it, what if they saw it written the other way? What if it said 1s2, 2s2, 2p3? What element would that be?
Well, that's got 2 electrons in 1s, 2
Right.
electrons in 2s, so that's 4 electrons, and 3 electrons in 2p. That's 4 plus these 3 makes 7.
7.
That's nitrogen.
Right, so we got, and if we finish this and made it not boron anymore, we'd have our other 2 electrons there, and we can write it like this, or like this.
Well, why didn't you just put 2 here?
Oh, no, no.
Why didn't
no,
you just go up, down, up?
You can't do that.
Whose rule is that?
That's Hund's rule.
Hund's rule.
Like, you know, I talked to my class about the dressing rooms. You don't want to go to the mall and try on a bunch of clothes and have to share a dressing room.
That's
Ew.
creepy.
It is creepy.
Yeah.
And, you know, if you have, you know, go to visit grandma's house for the holidays and all the cousins are there and you have to share bedrooms, if you can get your own bed or cot, you'd rather have your own, right? Instead of having to share. Well, if the electrons have an available orbital, easy for me to say, to go into, they're going to want to have their own space. Their
Yes.
own space until they have to double up and share.
Right.
All right.
33 is actually Hund's rule,
Right.
which is what we just did.
Mm-hmm.
We just worked on Hund's rule about
Right.
1 electron per orbital before you double up.
Right. So it's nice we kind of killed
Yeah.
2 test hints
You
with
betcha.
one explanation. So 34, what makes an electron configuration stable? So how can we tell when we look at the electron configuration written out if that's stable? Well, what makes an atom stable? What does it want to get?
A noble gas
A
configuration?
noble gas configuration which has how many electrons?
Well, it's usually 8.
Yeah, it is.
In the valence energy level?
In the valence energy level, there's a couple exceptions to that, but they want 8.
Yeah, they want to be full.
So they'd always end up in what block on the periodic table? The full ones.
Yeah, according to my custom colored periodic table,
Mhm.
it's the P block.
The P block.
Mm-hmm.
And when we went over in those energy levels from the S and the P electrons, which are valence electrons, there's 2 in the S and 2, 4, 6 in the P.
Mm-hmm.
That gives us 8 electrons in the valence shell.
You betcha.
So to be stable, the best example of stability is to have 8 electrons in the valence shell. We talked a little bit about some exceptions to that, and I believe coming up in another test hint, we'll have some questions about the exceptions. So let's hold off
Yeah,
until then.
we'll get there. Number 35.
Never mind, it's right here.
It's right here. Why there are exceptions to the Aufbau principle for elements such as chromium and copper.
Right.
And these exceptions come exactly right back to what Mrs. Gregory was saying in stability. And when you start to pile more and more electrons into the electron cloud,
Right.
there are some situations that can arise where the atom is going to find stability in different places, because you have so many different sublevels and orbitals.
Right.
There's a couple different ways to do that. You want to write one out?
So if the atom can get 8 electrons in its outer shell, that's the best of the best. But sometimes that doesn't happen. Let's do one with a D.
Okay. 1s, 2s, 2p,
Yep.
3s, 3p, 4s, and 3d. Oh, there's 5.
There's 5.
Yes.
Remember, there can be 5 d orbitals, so we have 5 spots in our orbital diagram for that. We missed an s here.
Oh.
We've got 1 for each of our s's, and we have 3 spots available for the p.
We did a whole worksheet. This was transparency number 10.
Yes.
We did a whole worksheet dealing with this issue, this sort of out of orderness.
It's out of order. It's called something by OO, orbital overlap.
Yes.
Orbital overlap. Those energy levels are so close together, the farther out you get from the nucleus, that they do kind of overlap a little bit. And where are we going with this? Oh, the exceptions. So Aufbau says we're going to fill from the lowest energy levels first. So we got all this stuff down here filled in. And Mr. Suston, following Hund's rule, 1 electron in each orbital.
Okay.
All right, well, let's keep going.
Okay. So
And we put, that would be
1
potassium, calcium,
potassium, calcium, the edge of the S block.
yeah,
And then
scandium, with
scandium,
21st electron,
vanadium,
titanium,
titanium, and then vanadium.
then vanadium,
Sorry, I'm a loser. I'm a loser that I know that.
and then chromium.
Okay, so chromium's last electron here should go here.
Right. But,
And
go ahead.
the way I explain it is, here's all of these electrons. You have this very high energy, complicated, crazy, double peanut orbitals,
thing.
very high energy.
Oops, I broke.
This energy level is so close
Yeah.
to being completely filled that the whole electron cloud kind of gets a little stressed out.
Right.
And in order to reach some stability,
Right.
this highest energy sublevel reaches down and picks the pocket of 4s,
Oh yeah.
which is lower in energy.
Technically, right. Just a little bit.
Yeah. And pulls that electron up here. And now we have these highest energy orbitals are now half filled.
Half filled. So if we can get 1 electron in each of those orbitals, they can't be double because there's not enough electrons, but if we can at least get 1 in each, then that's the next best arrangement for stability. Okay?
And that only happens when we get into this position where we have very high energy orbitals
Right.
that are nearly
Nearly.
half filled or nearly filled.
Right.
Right.
So if they're that close and they can get an electron to move over there, then they will. All righty. Well, next page.
Next page. It's a short test.
It is a short, well, it's only half the test.
Well, you know,
Okay.
to hear them complain about it, I think it was the end.